Welcome to Relaxing Wisdom. Tonight, let yourself sink slowly into something very old. There is no need to hurry. There is nothing here that will startle you, nothing that will demand you stay sharp or sit up or hold on tight. This is a story about the slowest thing that has ever happened on this planet, and the kindest way to listen to it is the way it actually unfolded, slowly, quietly, over a length of time so vast that the human mind can only brush against it, the way a hand brushes against the surface of deep water without ever touching the bottom. So settle in. Let your shoulders come down. Let the day you carried go soft at the edges. I want to begin not with a map and not with the great cracking apart of the world, but with a single leaf. It was not a green leaf. It had not been green for a very long time. It was a leaf turned to stone, pressed flat into dark rock, its shape preserved with such patience that you could still see the long tongue-like blade and the fine veins running through it like the lines on the palm of a hand. The leaf belonged to a plant called Glossopteris, a seed fern from a world that no longer exists, and the strange thing about this leaf, the thing that would eventually rearrange how we understood the entire planet, was where it was found. Because it was not found in one place, it was found on 5. On Glossopteris, that same fossilized leaf, that same ancient plant, has been pulled out of the rock in South America, and in Africa, and in India, and in Australia, and perhaps most hauntingly of all, in Antarctica. 5 continents, 5 great pieces of land now separated by thousands of miles of cold, open ocean, and yet the very same plant grew on all of them and left its fingerprints in the stone of all of them, as though it had never known there were oceans at all. And here is the part that made this a true mystery, a real one, the kind that scientists could not simply wave away. The seeds of Glossopteris were large, too large and too heavy to be carried by the wind, too large to drift across an ocean and wash ashore on a distant continent and take root. These were not the light, floating seeds of a dandelion that the breeze can lift and scatter for miles. These were heavy seeds, the kind that fall close to the parent plant, the kind that stay home. They could not have crossed the sea. There was no mechanism, no current, no wind, no bird, no possible way for the same plant to seed itself onto 5 continents separated by deep, salt water. And so the leaf, this quiet little leaf in the rock, was asking a question that nobody could answer for a very long time. If the seeds could not cross the ocean, then how did the same plant come to grow on lands that the ocean now keeps apart? There was only one answer that made any sense at all, and it was an answer so strange that for decades the people who proposed it were laughed out of the room. The answer was this: the lands had not always been apart. Once, long ago, they had all been joined. The 5 continents where Glossopteris grew had once been a single, continuous stretch of ground, and the plant had simply spread across that whole stretch the way any plant spreads, slowly, generation by generation, into the soil next door. The oceans came later. The oceans came in between. The plant did not cross the water. The water arrived after the plant was already there, and it pulled the land apart beneath it and stranded the same leaf on shores that would drift away from one another for 200 million years. That is the idea I want to carry you into tonight. The idea that the world was once whole and then it came apart very slowly, and that the coming apart was not only a story about rock and water, it was a story about life, about living things being separated from their own kind by the patient widening of the sea. But before we go any further into that, I want to stay with the leaf a moment longer, because there is something about how that Antarctic leaf came to be known that I have never been able to forget. And I think on a quiet night like this, it is worth telling slowly. The Glossopteris fossils in Antarctica were carried out of that frozen continent by men who were dying. In 1912, a British expedition led by Robert Falcon Scott was making its way back across the Antarctic ice. They had reached the South Pole only to discover they had been beaten to it, and now they were walking home across one of the most merciless landscapes on the planet, hauling their sledges by hand through cold that does not forgive. They were exhausted. They were starving. The weather had turned against them. And they were, though some of them surely knew it by then, not going to make it. And yet, on that return journey, with the cold closing in and their strength draining away, these men stopped to collect rocks. Geological samples, stones from the mountains they passed. Among those stones were fossils of Glossopteris, the seed fern, leaves pressed into rock from a time when Antarctica had not been a white desert of ice at all, but a temperate land where forests grew. The men did not abandon these stones to save weight, though every ounce they carried cost them something they could not spare. They kept them. They dragged that rock across the ice as the ice took them, one by one. When their bodies were found months later, the rocks were still with them. The Glossopteris leaves were still there, beside the men who had carried them to the very end. And in time, those fossils helped prove what the dying men could not have fully known they were carrying. They were carrying evidence that Antarctica had once been warm, that it had once been joined to other lands, that the frozen graveyard at the bottom of the world had, in the unimaginable past, been a green country where the same fern grew that grew in India and Africa and South America. There is something about that on a still night that settles into the chest. The thought of a leaf that travelled across the deep past by simply staying where it was while the world moved underneath it. The thought of men who froze in the act of bringing that proof home, the patience of stone and the fragility of the people who read it. So that is our first quiet clue, Glossopteris, a plant on 5 continents that should only have been on 1. And now, gently, I want to ask you the 3 questions that sit at the heart of everything we will wander through tonight. They are the questions that the leaf and the rock and the moving world all press upon us.
How did the continents move? We feel the ground beneath us as the very definition of solidity. The phrase we reach for when we want to say something is unshakable is that it is set in stone, that it is firm as the earth itself. And yet the earth is not firm. The continents have wandered. The ground we trust to stay still has crossed oceans. How?
How do we know? Because this is not a guess, and it is not a story someone simply decided to believe. We were not there to watch it. No human eye has ever seen a continent cross a sea, because no human life is long enough to see even a single step of that walk. So how could anyone ever prove that the lands had moved? What evidence, locked in rock and bone, could possibly tell us that the world had been rearranged? And finally, the question that I find the most beautiful of all, why does it matter for the living? Because here is the secret the leaf was whispering. When the continents drifted apart, they did not only move rock, they moved life. They took living populations of animals and plants and they tore them in half, and they carried the 2 halves away from one another, slowly, across millions of years, until each half forgot the other existed. And in that long forgetting, each half became something new, something its cousins across the water would no longer recognize. That is the idea I most want to leave with you tonight, and we will return to it again and again, gently, like a tide coming back to the same shore. We usually think of the drifting of continents as a story about geography, about the shapes on a map, but it is something far stranger and far more alive than that. The drifting of the continents is one of the great engines of evolution itself. When a moving piece of land splits a population of creatures in two, the two halves can no longer breed with each other. They are sealed off, each on its own ship of stone, and they begin to change in their own directions, shaped by their own new world. Given enough time, and the world gives almost unlimited time, they become entirely different kinds of creature. Drift is not the backdrop against which life evolved. Drift is one of the hands that did the shaping, the slowest, grandest act of separation the living world has ever undergone. Continents as ships, and the life aboard each one quietly becoming unrecognizable to the family it left behind on the far side of the widening water. We will follow that idea all the way to its ends tonight. We will find the marsupials marooned in Australia, where a whole continent forgot what a wolf was and then built one from scratch with a pouch. We will find the lemurs sealed onto the island of Madagascar, an ark of creatures that exist nowhere else on Earth. We will follow one piece of land, India, on the fastest journey any continent has ever made, racing north across an entire ocean to crash into Asia and lift the roof of the world. And we will stand eventually at the very top of Mount Everest, the highest point on the planet, and find there, in the rock, the fossils of sea creatures lifted out of a vanished ocean to the sky. But not yet. There is no need to rush toward any of it. We have all the time the night will give us, and the story is sweetest taken slowly. Before we go deeper, I would love to know where in the world you are listening from tonight. Whether you are somewhere with snow at the window, or somewhere warm and humid, or somewhere the city never quite goes dark, leave a word in the comments if you feel like it, and tell me where you have settled in to rest. There is something fitting about it, on a night when we are talking about how the world was once all joined together. We are scattered now, all of us, across the same drifted continents this story is about, and yet here we are, gathered in the same quiet place for a little while. And if you are new here, and you find that this slow kind of journey helps you drift off, you are very welcome to subscribe, so there will always be another one waiting for you whenever the night is long. But none of that is the point right now. The point right now is simply to rest and to listen and to let the old world unfold. So let us go back to the beginning. Not the beginning of the leaf, but the beginning of the whole, the time when there were no separate continents at all. Roughly 335 to 300 million years ago, all of the land on Earth was gathered together into a single, enormous mass. Not several continents close together. One great supercontinent, a single body of ground so vast that you could, in principle, have walked from what would one day be the northern reaches of Canada all the way to the southern tip of what would become Africa or South America without ever once crossing a sea. There was nowhere else to go. There was only the one land surrounded on every side by a single world-wrapping ocean. We have a name for that gathered-together land, and the name itself is a kind of poem. We call it Pangaea. The name was given to it by a German scientist named Alfred Wegener, and he built it from Old Greek roots, pan meaning all, Gaia, the ancient word for the earth, the land, the ground itself, Pangaea, all earth, the whole world, all of it, drawn together into one. It is, when you sit with it, a remarkably tender name for something so colossal. All the land that there is, all of it, held in one piece, with one great ocean wrapped around it like a sea around a single island the size of a planet's worth of ground. And that ocean had a name too, or at least we have given it one. We call it Panthalassa, again from the Greek. Pan, all, thalassa, the sea, the all-sea. One ocean for one land. A world far simpler in its shape than the cluttered, scattered world we know now, with its 7 continents and its many seas. Back then it was just the two great things, the one land and the one water, all earth and the all sea, wrapped around each other in the deep past. But Pangaea, for all its vastness, was not permanent. Nothing on this scale ever is. For something like 100 million years or more, the supercontinent held together a single mass of ground. And then, beginning around 200 million years ago, in the early stretch of the period we call the Jurassic, Pangaea began, very slowly, to crack. I want you to imagine that as gently as it actually happened, because the words we use, cracking, breaking, splitting, all sound violent, and the reality was anything but. There was no sudden shattering. There was no single day when the world broke apart. The fracturing of Pangaea was the slowest event you could possibly conceive of. It happened at a speed so gradual that on any human timescale, on the scale of a single life, or 100 lives, or 1,000, nothing at all would have seemed to be happening. The ground would have looked utterly still. The coastlines would have looked utterly fixed. A person could have lived an entire life on the shore of Pangaea as it was beginning to come apart, and died of old age, and their grandchildren could have died of old age, and the land would not have moved far enough for anyone to notice. How slowly do the continents move? Here is the comparison that I find the most soothing of all, and I offer it to you tonight precisely because it is so quiet and so close to home. The continents move at roughly the speed your fingernails grow. That is all, a few centimeters a year. The Atlantic Ocean, even now, even tonight, is widening by about 2.5 centimeters every year, which is just about the rate at which the nail on your finger lengthens. Right now, as you lie there, your fingernails are growing, slowly, imperceptibly, and at very nearly that exact same pace, the continents of the Earth are drifting across the face of the planet. North America and Europe are easing apart at the speed of a growing nail. You will never feel it. You will never see it. But it never stops. It has not stopped for 200 million years. There is something deeply restful in that, I think. The idea that the most enormous movement in the history of the planet, the rearrangement of all its land, happens at the speed of something so small and so familiar that you could not possibly perceive it. The world is moving beneath you right now, and it is moving as gently as your own body keeps its quiet work going while you sleep. The continents are drifting at the pace of fingernails and breath. Nothing is rushing. Nothing ever was. So Pangaea began, at that fingernail pace, to come apart. And the very first thing it did was split into two great halves. The northern half drifted slowly in one direction. It carried within it the future shapes of North America and Europe and most of Asia. We call this northern half Laurasia, and the southern half drifted in its own direction, carrying the future South America and Africa and Antarctica and India and Australia and Madagascar and Arabia, all still joined together, all still one body of southern land. We call this southern half Gondwana. Laurasia in the north, Gondwana in the south. The two great daughters of Pangaea, each beginning the long journey that would, in time, scatter the world into the map we know. And between them, as they parted, the sea came in. A new ocean opened in the widening gap between Laurasia and Gondwana, a sea we call the Tethys. Keep that name somewhere soft in your mind, the Tethys, because much later in our story, this ocean will do something extraordinary. This ocean will, in the deepest of all time's strange reversals, be lifted up out of existence and carried to the top of the highest mountain on Earth. But that is far ahead of us. For now, simply hold the picture. The one land cracking into two, the northern half and the southern half drifting apart. And a new sea, the Tethys, flowing quietly into the gap between them. Now I told you that the leaf, the Glossopteris, was our first clue, but it was not the only one. And I want to give you a second clue tonight before you drift too far. because it is one of the most elegant pieces of detective work in all of science, and it has the same quiet, irrefutable beauty as the leaf. This second clue is a small animal, a little reptile only about a meter long that lived in the early part of a period called the Permian, long before the dinosaurs in the deep ages near the end of Pangaea's wholeness. Its name is Mesosaurus. It was not large, it was not fearsome. It was a slender, swimming reptile with long, thin jaws full of needle-like teeth, and it spent its life in water. And here is the crucial thing about Mesosaurus, the thing that makes it such a perfect little witness to the moving earth. It lived in fresh water, not the sea. Mesosaurus made its home in lakes and rivers and freshwater basins. It was not a creature of the salt ocean. It could no more have lived in the open sea than a goldfish could live in the Atlantic. Now, the fossils of this small freshwater reptile have been found in exactly 2 places on Earth. They have been found in southern Africa, and they have been found in eastern South America, and nowhere else, just those two regions on 2 different continents, separated today by the entire width of the South Atlantic Ocean. Thousands of miles of deep, salt water sit with the problem that creates. Here is a freshwater animal, an animal that could not survive a journey across a salt ocean, found on both sides of a salt ocean and nowhere in between. It could not have swum across, the salt water would have killed it. It could not have been carried across, it lived in lakes, not on driftwood. There is no honest way to explain how the very same freshwater reptile came to live on 2 continents, separated by an ocean it could never have crossed. Unless once there had been no ocean there at all. Unless southern Africa and eastern South America had once been pressed together, edge to edge, a single, continuous stretch of land, with freshwater lakes and rivers that spread across both, with no salt sea dividing them, so that a small freshwater reptile could swim freely from what is now one continent into what is now another, never once leaving the fresh water it needed, never even knowing that one day an ocean would open beneath its descendants and carry the 2 shores apart. That is what Mesosaurus tells us, that those 2 coastlines, the eastern edge of South America and the western edge of Africa, were once a single shore, that the basins of fresh water were continuous across them, that a little swimming reptile going about its small life in some Permian lake was living on what would later become 2 separate continents, in a world where, for it, they were simply one place. And it fits, doesn't it, with what your eye may already have noticed if you have ever looked at a map of the world. The way the bulge of Brazil, the great rounded shoulder of eastern South America, seems to nestle so neatly into the curve of Western Africa, into the dip of the Gulf of Guinea, the way 2 torn pieces of paper still carry the matching shape of the rip between them. People noticed that fit a very long time ago, long before anyone could explain it, and the little freshwater reptile lying in the rock on both sides of that torn edge was the quiet proof that the fit was real, that those 2 shores had truly once been joined, that the puzzle pieces were not just similar in shape by chance, but had genuinely been broken apart from a single whole. So now you have 2 witnesses, the leaf and the reptile. Glossopteris, the seed fern whose heavy seeds could not cross water, found on 5 continents that the ocean now keeps apart, and Mesosaurus, the small freshwater reptile that could not survive the salt sea, found on 2 coastlines that the salt sea now divides. 2 creatures, a plant and an animal, both saying the same impossible thing in their own quiet voice. The lands were once joined, the oceans came later. The world was whole, and then it came apart slowly at the speed of growing nails, and the living things that had spread across the whole were left stranded on the pieces. And this, my friend, is where the story truly begins to open out, because once you accept that the world was once one and then divided, a question rises up that is far larger than any single leaf or any single reptile. If the continents tore apart and if they carried living populations with them, sealed off from one another by the widening water, then what happened to all that life over the millions of years that followed? What becomes of a population of animals when their world is cut in two and the halves are carried away from each other for 100 million years? The answer is the heart of everything I want to share with you. The answer is that each piece of land, each drifting fragment, became its own separate world, its own private experiment in what life could become. And on each one, given the gift of isolation and the gift of time, evolution wandered off down its own strange and lonely path until the creatures on one fragment became things that the creatures on another fragment, their own distant cousins, would never recognize as kin. But before we follow those scattered creatures, before we sail with the marsupials toward Australia and watch the lemurs raft across the sea to Madagascar, we have to do something quieter first. We have to understand how anyone ever came to believe this at all. Because for a very long time, the idea that the continents could move was treated not as a beautiful truth, but as a kind of foolishness. The man who first truly argued for it, the same man who gave Pangaea its tender name, spent his life being dismissed and ridiculed, and he died out on the ice, in the cold and the dark, decades before the world finally admitted that he had been right all along. His name you already know, Alfred Wegener. And his story, the story of how he saw the truth that the leaf and the reptile were whispering, and how he was disbelieved for it almost to the end, is where we will go next, gently, as the night deepens around us, and the slow old world keeps turning beneath us at the pace of a growing nail, carrying us all, as it has always carried everything, toward shores we will never live long enough to see. Alfred Wegener was born in Berlin in 1880, and he grew up to become the kind of man who noticed things, not in a hurried way, not the way someone solves a puzzle and moves on, but in the slow, patient way of someone who senses a shape beneath the surface of the world and cannot stop touching it with his mind until the shape becomes clear. He was trained as an astronomer, a meteorologist, which gave him the particular gift of thinking across vast scales, of being comfortable with distances and time spans that ordinary daily life never asks us to hold. And it was this gift, this ease with the enormous, that allowed him to look at the map of the world as it was drawn and feel something that most people had simply never paused to feel, that the whole thing looked wrong. Not wrong as in mistaken, wrong as in incomplete, as if someone had broken a single thing into pieces and then, in putting them back down, had laid them just slightly apart from where they truly belonged. He was not the first to feel this. There had been others before him, much earlier, who had noticed the same strangeness in the coastlines. Francis Bacon, the English philosopher, wrote about the similarity between the African and South American coastlines as early as 1620, the fit between the Great Bulge of Brazil and the cupping curve of the Gulf of Guinea, two shores that seemed to reach toward each other across the width of the water that now lay between them. And before Bacon, the Flemish cartographer Abraham Ortelius, in 1596, had drawn the same inference even more plainly, suggesting in print that the Americas had been torn away from Europe and Africa by earthquakes and floods. These were not foolish men, these were careful observers, looking at the map of the world and feeling the same quiet wrongness Wegener would feel 3 centuries later. But noticing is different from arguing. Bacon and Ortelius noticed. Wegener argued. He took the noticed shape and tried to build a case for it, to find everything in the world's record that supported it, to gather the evidence and weigh it, and lay it out so that it could not be easily ignored. This was the great project he set himself quietly, beginning around 1910, when the shape on the map would simply not leave him alone. He called it continental displacement. The idea, as he first stated it publicly in 1912, was that the continents had not always occupied the positions they occupy now, that they had once been gathered into a single, enormous whole, and that they had moved over immeasurable time to reach the arrangement we know today. In 1915, he published the full case in a book, The Origin of Continents and Oceans. It was a careful, thorough, deeply observed work, assembled from many different kinds of evidence. The shapes of the coastlines, yes, but also the fossils, the matching geological formations, the records in the rock of ancient climates that made no sense given where the rocks now sat. Taken together, he believed the evidence was overwhelming. He believed it was not possible to look at all of this and conclude anything other than that the continents had moved. The scientific world, almost without exception, disagreed, not politely and not quietly. He was dismissed, mocked, and ignored. Geophysicists in particular were merciless. Their argument was not with his evidence exactly, but with his mechanism. He could show that the continents looked as though they had once been joined. He could show fossils on the wrong continents, mountain ranges that matched across the ocean, ancient glacial scratches in the rock of warm countries pointing outward from where a southern polar ice cap would have been if the continents had once been clustered differently. He could show all of that, and he showed it very well. But what he could not show was how. He could not identify a force sufficient to drag an entire continent across the surface of the Earth. And without the mechanism, the establishment decided the whole idea was simply not credible, no matter how elegant the evidence. One American geologist described it as a fairy tale. Others were less charitable. Wegener continued. He refined the arguments, updated the evidence, published new editions of his book in 1920, in 1922, and again in 1929. He kept working, kept pressing, kept pointing at the leaf and the reptile and the mismatched mountain ranges, the tillites in India, the glacial scratches on the ancient basement rock of Africa, all of it whispering the same quiet message. This was once somewhere else. He gathered more of the matched fossil record, adding to what Mesosaurus had already told him, following the thread of the same story through other creatures. There was Synognathus, a Triassic land reptile, a solidly built predator, something like a large dog, that left its bones in the rock of South America and Africa, on opposite shores of what is now the South Atlantic, with no route between them that a land animal could have walked. And there was Lystrosaurus, a creature with an almost surprising abundance of its kind, a stocky, plant-eating therapsid, something between a reptile and a very early mammal, with a blunt, squared-off face, built low to the ground and probably quite common in its time, the way some animals become common when conditions suit them well. Lystrosaurus is one of the most abundant large land vertebrates known from the period immediately following the Permian extinction, the great dying that ended the Permian period around 252 million years ago and very nearly ended complex life on Earth. Lystrosaurus, remarkably, had survived it, and when it reappeared in the fossil record after that catastrophe, it appeared not in one place but in three: Africa, India, and Antarctica. Three land masses now separated by enormous distances of ocean, all of them holding the bones of the same squat, inelegant little survivor. And each time Wegener added a creature, the case grew heavier, and the dismissals grew louder, because the louder the dismissals, the clearer it became that the scientific objection was not really to the evidence. It was to the idea that the ground beneath us was not fixed. It was to the deep human and the deep scientific discomfort of a world that refuses to stay still. We have always preferred to believe that the Earth, at least, is permanent, that whatever else shifts and changes, the land will hold. Wegener was asking people to give up that permanence, and they were not ready. The year 1930 arrived. Wegener was 50 years old. He had spent the better part of 2 decades trying to convince the world that the continents had moved, and the world had spent the same 2 decades declining to be convinced. He went to Greenland that autumn on a scientific expedition, work that had nothing to do with continental drift, meteorological fieldwork, the kind of patient measuring and observing he had always done. In November of that year, on the ice sheet, he died. The exact circumstances are not entirely clear. He was last seen alive on November the 1st, his 50th birthday, as it happened, leaving a supply camp to cross back to the coast. He was found months later, some distance from the camp, still on the ice. He died out there, on the cold and silent surface of the Greenland ice sheet, with the world's refusal still echoing around him, still waiting for the vindication that would not come for decades. It is one of the quiet tragedies of the history of science, the man who was right, dying in the cold, his idea still dismissed as a fairy tale, while the evidence he had gathered kept silently accumulating, kept waiting, undisturbed, in the rock and the fossil beds and the bones of the matched creatures on their separated shores. The vindication came, but not for Wegener. It came for his idea, which is not quite the same thing, though perhaps it is the best that ideas can hope for, to outlast the person who held them and be proven right in the fullness of time. What finally settled the question was not any new fossil, not any new creature found in the wrong place, not any more beautifully matched mountain range or ancient glacial scar. What settled it was something that happened to be discovered in the deep oceans in the 1950s and 1960s, something nobody had been able to observe before simply because the tools to observe it did not yet exist. The seafloor had been mapped, and what the mapping revealed was a system of ridges running through the ocean basins like the stitched seam of a great planetary wound, a mid-ocean ridge system, the most dramatic of which runs down the length of the Atlantic in a kind of wavering S-curve, from the north to the south, equidistant from the opposing coastlines on either side. And along the flanks of this ridge, in the rock of the ocean floor, there were stripes, magnetic stripes, alternating bands of rock with opposite magnetic orientations running parallel to the ridge on both sides of it, each band mirroring the corresponding band on the other side of the ridge exactly, as if reflected in a very long, very still pool of water. The reason for the stripes was the behavior of iron-bearing minerals in molten rock. When new oceanic crust forms at the ridge, upwelling from below as the plates on either side pull apart, the molten material cools, and as it cools, the magnetic minerals in it lock on to the orientation of Earth's magnetic field at that moment, the way iron filings align with a magnet. They record the field as it was when the rock solidified, and Earth's magnetic field, it turns out, periodically reverses itself, north becoming south, south becoming north, on timescales ranging from tens of thousands to millions of years. These reversals are recorded faithfully in the rock as it forms and spreads outward from the ridge. The result is a timeline written in magnetism, symmetrically on both sides of the ridge, reading outward from the center. This crust formed when the field was in this orientation, then this band formed when it reversed, then this one when it reversed again. The stripes are a perfect calendar of ocean floor creation. And because the calendar runs in both directions, away from the ridge on both sides, it proves unambiguously that new ocean floor is forming at the ridge and spreading outward, carrying whatever sits on top of it, continents included, along with it as it goes. This was sea floor spreading, and the paleomagnetic evidence for it was not a matter of interpretation or inference or matching shapes on a map. It was direct, measurable, reproducible, symmetric. The mid-Atlantic ridge was not a scar but a seam, not a wound but a place of making, generating new ocean floor at a pace of roughly 2.5 centimeters a year, year after year, century after century, carrying the Americas westward and Europe and Africa eastward, widening the ocean between them by about the width of a finger each year and the length of a room in a human lifetime. The continents were moving. Wegener had been right. With the mechanism of seafloor spreading understood, the force that had eluded Wegener could finally be filled in. The continents do not push themselves around the surface of the Earth by any force applied from behind them. What pulls them primarily is their own cold and heavy leading edges, where oceanic crust meets a continent, or where two oceanic plates converge. The denser oceanic crust sinks back into the mantle, dragged down by its own weight, and as it sinks it pulls the rest of the plate behind it, the way a tablecloth pulled from the edge of the table by its own weight would drag what lay on top of it slowly toward that edge. And this is slab pull. It is the single greatest force driving plate motion, supplemented by the ridge push of the spreading centers and by the great slow churning of the mantle below, the heat-driven circulation called mantle convection, hot rock rising at the ridges and cool, dense rock sinking at the subduction zones, the engine at the heart of the whole planetary process. And with the mechanism understood, the deeper picture could be assembled, not just the proof that the continents had once been joined, but the whole enormous history of how they had arranged and rearranged themselves over the lifetime of the planet, a history that reaches back not merely to Pangaea, but far, far beyond it. Pangaea was not the first. This is something important to understand, something that takes a moment to settle into, because we tend to speak of Pangaea as though it were the original configuration of the Earth, the one true whole from which everything else was a departure. But it was not original at all. It was simply the most recent gathering, the last supercontinent, the latest in what turns out to be a rhythm as deep and regular as breathing, continents assembling and fragmenting over and over again across the billions of years of the Earth's existence. Before Pangaea there was Rodinia, whose name comes from the Russian word for homeland, Rodina, assembled around 1.1 billion years ago and began to fracture somewhere between 750 and 800 million years ago, breaking apart into the pieces that would drift and wander for hundreds of millions of years before gathering again to form the next configuration, which was Pangaea. And before Rodinia there was Columbia, sometimes called Nuna, assembled perhaps 1.8 billion years ago. And before Columbia, others still dimly visible in the deep rock record, all of them telling the same story of the Earth's surface in constant, slow planetary rearrangement. The pattern is called the supercontinent cycle, and its rhythm, though variable, seems to run on a time scale of roughly 300 to 500 million years from one gathering to the next, driven by the same engine of mantle convection and slab pull that drives it today. The continents drift apart until the subduction zones around the perimeter of the dispersed ocean bring them back together again, closing the ocean and piling the land into a new whole, and then the heat accumulating beneath the assembled supercontinent eventually drives a new episode of rifting, tearing the giant landmass apart to begin the cycle again. This is the tempo of the Earth, far too slow for any human sense of time to feel, far too steady and ancient to be called anything as dramatic as an event. It is simply what the surface of the world does. It assembles and disperses, carrying the living and the dead along on its slow rides, and in doing so has shaped every feature of the world we recognize as home. When Pangaea existed fully assembled around 335 to 300 million years ago, it was not a static thing. It was already subject to the forces that would eventually break it. The single enormous ocean that surrounded it was called Panthalassa, meaning all sea, a vast and ancient water that covered most of the hemisphere, not occupied by the supercontinent, an ocean so large that it dwarfed anything on the modern Earth. And within Pangaea, between its northern and southern portions, an embayment of ocean had already formed, a large triangular gulf of sea pushed in from the east between what would become Europe and Asia to the north, and Africa and Arabia to the south. This was the Tethys Sea, ancient and warm, the ancestral Mediterranean, and far more, the ocean that would in time be pushed and squeezed and eventually all but destroyed as the pieces of Gondwana came charging northward to close it. Pangaea was not a structurally simple object. From very early in its history, it had a kind of natural division, a latent fault line written in its geology between its northern half, the aggregate of what would become North America, Europe, and Asia, and its southern half, which would become South America, Africa, India, Antarctica, Australia, and the island of Madagascar. Geologists call these two halves Laurasia in the north and Gondwana in the south, and even before the final breakup of Pangaea as a whole, you can see the seam between them, the Tethys embayment widening, the two halves beginning to feel the different pulls of the mantle currents moving beneath them. Gondwana itself was an ancient thing, older than Pangaea in some respects, recognizable as a coherent southern landmass for hundreds of millions of years before Pangaea assembled around and incorporated it. The name comes from the Gondwana region of central India, where the geologist Melchior Neumayer first noted in the 19th century the distinctive geological character shared across the scattered southern landmasses, the ancient basement rock, the coal-bearing sedimentary sequences, the distinct fossil flora of Glossopteris. Gondwana was already carrying its own identity, its own signature in rock and leaf, long before it began to come apart, and now lying in the quiet of whatever room holds you tonight, you can take a moment to picture it. Close the modern maps in your mind, remove the Atlantic, remove the Indian Ocean, pull Australia up beside Antarctica, press Antarctica against the southern tip of South America, fold India back against the eastern coast of Africa, slot Madagascar into the gap between Africa and India, fit South America back against the Gulf of Guinea, and let Greenland and North America ease back across the closing ocean to press against the northwestern coast of Europe. Do all of that, and you have something like Pangaea, a single vast continent straddling the equator and reaching from the North Pole toward the south, surrounded by the one great ocean with the warm wedge of the Tethys Sea already nibbling into its eastern side. Enormous, improbable, real. Sit with it for a moment. The world as it was when the first dinosaurs were just beginning to appear in the early part of the Triassic, when the supercontinent was beginning, very slowly, to feel the pull of its own ruin. This is the ground state from which everything that follows flows, and to understand why the living world looks the way it does today, why certain creatures are found only in certain places, why the fauna of Australia seems to have arrived from a different planet than the fauna of Europe or North America, you need to hold this picture in mind. One world, one landmass, one life. Everything connected. Every shore reachable from every other shore by land. And then, slowly, the connections beginning to fail. The evidence of that connectivity, written in the fossil record long before any of the modern machinery of geology existed to confirm it, was what Wegener had been trying to explain with his life's work. He was right about the connectivity. He was right about the movement. He lacked only the mechanism, the language for the engine that drove it, and that language came after he was gone. What he saw, what he kept pointing at across all those years of dismissal, was that the world's rock and fossil record was telling a single coherent story across the oceans, if you were willing to look. The same mountain belts interrupted by the Atlantic, reading like a sentence cut in half by someone who had torn the page down the middle. The Appalachian Mountains of eastern North America, their ancient roots running from Alabama to Newfoundland, and across the ocean in exactly the positions the fit of the continents would predict. The Caledonides of Scotland and Scandinavia, same age, same rock, same deformation history, the one a continuation of the other, the two halves of a single range separated by a few thousand kilometers of ocean. And further still, their continuation in the Atlas Mountains of Morocco, North Africa, where the same ancient orogeny laid down its records in the same rock. One range, One event, three continents. And in the ancient rock of India and of Central Africa and of South America and of Antarctica, there are the tillites, thick deposits of lithified glacial debris, the crushed and gouged and tumbled rock left behind by glaciers when they move, containing within them the peculiar boulders called drop stones, too large to have been carried by water, dropped from floating ice as glaciers carved into ancient seas. These tillites, now sitting in the tropics and the subtropics of the modern world, record in their chemistry and their texture the passage of immense ice sheets, sheets consistent in age and in direction across all four of those now scattered land masses, all pointing outward from a center where a south polar ice cap would have sat around 300 million years ago, when those land masses were all pressed together in the southern portion of Pangaea, and the South Pole lay at their common heart. To look at a glacial striation in the basement rock of Central Africa, a long, deep scratch made by ice dragging a stone across the rock surface hundreds of millions of years ago, and to find that same scratch's orientation, corrected for the movement of the continent, pointing toward the same vanished ice center as the striation in the basement rock of Brazil or in the exposed stone of Antarctica, is to feel the past click into place in the most precise and physical way imaginable. The ice did not know what continents would become of its record. It simply moved as glaciers do, dragging the stone, leaving its mark and then retreating. And the mark is still there, in rock that has since traveled thousands of kilometers from where the ice made it. All of this, the matched mountains, the matched fossils, the matched glacial deposits, the matched rock ages, and the matched mineral belts, was available to Wegener in the years he spent building his case. He saw the pattern with remarkable clarity. His 1915 book laid it out with a care and a thoroughness that his critics often failed to match in their dismissals. And what gave the matched fossils their particular force, in addition to Mesosaurus and the others, was not just that creatures appeared on the wrong continents, but that they appeared in precisely the rock layers and the geological contexts that the continental assembly demanded. If the continents had once been joined, then the fossils of the joined era would be shared, and those of the separated era would diverge. That is exactly the pattern in the rock. The shared fauna runs up to the point of separation, and then, in the layers above, the stories fork, each lineage going its own way on its own moving island. This is the deep reading of the fossil record that makes continental drift not merely a geological curiosity, but a fundamental fact of life's history. The rock does not just record where the creatures lived, it records when the connections failed. It records the moment of severance, and in recording the severance, it tells us, as precisely as any archive, when each fragment of the ancient world began its long voyage into biological solitude. Wegener felt this. He could not have known quite how deep the story ran, could not have known the full drama of the marsupials crossing the Antarctic land bridge, or the lemurs rafting the Mozambique Channel, or the terror birds standing 3 meters tall in the South American isolation, because much of that evidence had not yet been collected and assembled in his time. But he knew the principle. He knew that a moving continent was also a moving vessel, and that the life aboard it was, in moving, being separated from the life aboard the other vessels. He knew it was a story about living things, not just about rock. He knew, and he was dismissed, and he died, and the ice held him, and the world went on drifting without his knowledge of it for another 3 decades. And then the stripes were found in the seafloor, and the mechanism was understood, and the fairy tale became fact. There is something worth resting in for a moment in the particular shape of that story. The evidence was always there. The leaf was always on the 5 continents. The freshwater reptile was always in the matching rock layers on the 2 separated shores. The mountain range was always running from Alabama to Newfoundland to Scotland to Morocco, one seam across four now separated land masses. The scratches of the vanished glaciers were always in the rock of countries that are now tropical, all pointing toward the same ancient southern pole. The evidence had always been there, patient and material and quiet, waiting in the stone and in the fossil beds, available to anyone who looked carefully enough and was willing to accept what the looking revealed. It simply had to wait for a man with the right kind of mind to gather it, and then for the world to be ready to accept the gathering. That is how science often moves, not in sudden leaps but in slow accumulations, evidence piling up quietly while the prevailing assumptions hold their ground, until the accumulation reaches a point where the assumptions can no longer bear the weight. The continents had always been moving, the fossils had always been in the wrong place, the mountains had always been the same mountain. And when the seafloor stripes finally made the mechanism undeniable, the whole edifice of evidence that had been waiting, unhurried, in the rock, could finally be read as what it had always been: a single, coherent statement about the history of the world. The statement begins with a supercontinent, assembled from pieces that had themselves assembled and dispersed before, carrying on a rhythm as ancient as the solid surface of the Earth. It proceeds through the fracturing of that supercontinent, slowly, over millions of years, opening new oceans as old ones close, separating the land into pieces that drift away from each other at the pace of growing fingernails, each piece becoming, in its isolation, a separate stage for the drama of evolution. And it ends for now with the world as it is, 7 continents, 4 oceans, and a living world whose strangeness and diversity and particular geographic logic is, when you understand what caused it, not strange at all, but exactly what you would predict if you knew what the Earth had done. We are beginning now to trace that story through the life, to follow the pieces as they drift and to watch what happens to the living things they carry. The mechanism is understood. The proof is in the rock and the magnet and the matched creatures on their separated shores. The world was once whole, and the long, slow story of how it became the world it is, the story of each fragment drifting into its own destiny and the life upon it quietly becoming something the rest of the world had never seen, is the story that lies ahead of us in the coming hours of this night. It begins, as so many of the deepest stories do, with an opening, with a rift, with the moment when what had been one thing begins, almost imperceptibly, to become 2. The first opening was not dramatic. There was no explosion, no sudden catastrophe visible from any shore, because there were no shores yet of the kind we mean when we use the word. There was only the vast interior of Pangaea, the low-lying basins and the ancient river systems, the fern-covered flats and the first tentative forests of the Triassic, a world that looked, to any creature walking across it, simply like land without end. And yet somewhere in what is now the eastern seaboard of North America and the western face of northwestern Africa, the rock beneath the surface was beginning to thin. The mantle below was doing what it had done before, what it would do again, rising in slow convective columns, shouldering against the base of the crust, stretching it, heating it, pulling it apart at a rate so gradual that no living thing could perceive it in a single lifetime or in 1,000 lifetimes. The ground does not announce what it is doing when it is doing this. It simply does it in the dark over millions of years. This was the beginning of the Central Atlantic, and it happened approximately 200 to 180 million years ago in the period that geologists call the early and middle Jurassic, at the close of the Triassic and into the age that would come to define the word prehistoric in the popular imagination. The rift that opened here was not the first fracture in Pangaea's body. The supercontinent had already been pulling apart in places, already feeling the slow internal stresses that attend all such structures, but it was among the most consequential. Because before the ocean could open, before water could flood the gap and begin the long work of growing into what we now call the Atlantic, the Earth did something violent. It erupted. The Central Atlantic Magmatic Province, the CAMP, as geologists abbreviate it, was one of the largest volcanic episodes in the entire history of the planet. Not a single volcano, not a chain of mountains venting ash and lava, but a vast network of fissures and flood basalt stretching across what would become eastern North America, northwestern Africa, western Europe, and parts of South America, a belt of eruption that in its time covered an area of rock millions of square kilometers wide. The lava did not build tall cones. It poured out across the landscape in flat, spreading sheets, flow after flow, layer upon layer, building up basalt plains that in some places reached hundreds of meters thick. You can still see these rocks today. The Palisades along the Hudson River in New York and New Jersey, the great cliff of dark columnar rock that faces Manhattan across the water, are the frozen remnant of one of those ancient lava flows. The Watchung Mountains of New Jersey are another. Across the ocean in Morocco and Portugal and France, the same dark volcanic rock appears in the same layers, from the same event, from the same moment in time. But the camp was not merely a geological spectacle, it was a killing machine. The gases released by eruptions on this scale, sulfur dioxide, carbon dioxide, in quantities that dwarf anything human industry has produced or will produce in any foreseeable future, altered the atmosphere profoundly enough to trigger what we now recognize as the end Triassic mass extinction, one of the 5 largest such events in the fossil record. Perhaps half of all species then living disappeared. The large cruratarsans, the crocodile-line archosaurs that had dominated the land, were devastated. And into the ecological space they left behind, the dinosaurs expanded, diversifying explosively in the Jurassic that followed, becoming the animals we think of when we think of that word. The sauropods, the theropods, the long-necked vegetarians that moved like living bridges across the lowland forests, and the predators that moved among them. So the opening of the Central Atlantic, the first true widening of the gap between what would become the Americas and what would become Europe and Africa, was in the same geological moment the catastrophe that cleared the stage for the age of dinosaurs. The ocean and the extinction arrived together, as so often happens when the Earth reshapes itself on these scales. The violence that makes the new world also unmakes the old one, and the water came in. Slowly at first, perhaps only a narrow seaway, shallow and warm, more like a long inland sea than an ocean. The kind of thing you might cross in a day's sailing, except that there was nothing yet to sail it, no creature with that capacity, only the slow encroachment of salt water into what had been dry land, edging north and south as the rift widened, year by year, centimetre by centimetre. At the pace of growing fingernails, the gap that would become the Atlantic Ocean began its long career of growing. The Central Atlantic opened first between North America and Africa, between what would become Morocco and what would become Nova Scotia. But the full story of the Atlantic's opening is not a single event. It is a sequence, spread over more than 100 million years, and the different sections of that ocean opened at different times and in different ways, each with its own character and its own consequences for the life it separated. After the Central Atlantic had been widening for some tens of millions of years, the South Atlantic began to open. This was approximately 140 to 110 million years ago, in the Cretaceous, in the middle of the age of dinosaurs, in a world that was warmer than today and covered by shallow epicontinental seas that spread across what are now the interiors of continents. South America and Africa had been holding together along their southern margins even as the North had begun to separate, and when the South Atlantic finally began to tear, it did so in a way that geologists describe as unzipping from south to north. The southernmost tip of the two continents separated first, and the rift propagated northward over millions of years, like a seam slowly coming apart from one end. Think of it the way a long wound heals, not all at once, not from a single center, but in stages, the gap widening in one place before it has fully opened in another. The South Atlantic opened that way, and as it widened, it left behind evidence of its origin that persists to this day in ways that have enormous practical consequences for the modern world. Where the two continents had been joined, there were vast salt basins, enclosed, evaporating seas that concentrated salt into enormous deposits along the margins of both shores. When the ocean finally opened and seawater flooded in, those salt deposits were buried under the accumulating sediment and eventually under the organic material that would, over millions of years, become petroleum. The salt itself acts as a seal, trapping oil and gas beneath it. And so today, the petroleum-rich offshore basins of Brazil and the petroleum-rich offshore basins of Angola and Nigeria sit on opposite sides of an ocean, mirrors of each other in their geology, twins separated at birth when South America and Africa finally came apart. Oil workers drilling off the coast of Brazil encounter the same geological sequences, the same salt layers, the same rock types, as oil workers drilling off the coast of West Africa. The ocean between them is a reminder written in rock and carbon of the moment the two shores were one. And then much later, the North Atlantic opened as well. This was approximately 60 to 55 million years ago in the Paleocene and early Eocene, geologically recent, in the timescale we have been inhabiting tonight. This final stage of the Atlantic's opening separated Greenland and North America from Europe, completing the rift that had begun 200 million years earlier at the other end of the ocean. The North Atlantic opening was accompanied by its own volcanic episode, the North Atlantic Igneous Province, which contributed to the landscape of Iceland and the Faroe Islands and the basalt columns of the Giant's Causeway in Northern Ireland and Fingal's Cave on the Scottish island of Staffa. Ancient flood basalts, dark and geometric, lining the coasts that used to be joined. By the time the North Atlantic had opened, the ocean that bears the name Atlantic was essentially the body of water we know today, though narrower, still widening at its middle ridge, still growing at roughly 2.5 centimeters each year. The pace of a human fingernail, as it has been all along. Through all of this, while the Atlantic was opening in its three great stages from Jurassic to Paleocene, something else was happening on the other side of the world. The Tethys Ocean, that ancient warm seaway that had separated the northern arm of Pangaea from the southern arm that had lain between Laurasia above and Gondwana below like a wide, sun-filled corridor, was closing. As the Atlantic opened and widened in the west, the plates carrying the continents of Africa and India and Arabia moved north, and as they moved north, they consumed the Tethys before them. The ocean floor of the Tethys was subducting, diving beneath the Eurasian plate, carried down into the mantle, returning to the molten interior of the planet from which it had once been extruded. What had been open water became the Mediterranean, which is itself a remnant of the Tethys, a shrinking relic of an ocean that was once far larger, still being squeezed by the continuing northward movement of the African plate. The Persian Gulf, the Black Sea, the Caspian Sea. These are all, in different ways, the last pockets of a world ocean that once stretched from what is now Spain to what is now Southeast Asia. The trade at work here is one of the most fundamental in plate tectonics. One ocean opens in the west while another closes in the east, and the continents shuffle their positions accordingly. It is worth pausing here, in the dark and the quiet, and holding the full picture for a moment. The Atlantic, which we tend to think of as a fixed and permanent feature of the world. The blue water on the maps, the barrier, and the route between the old world and the new is a young ocean, still growing, still widening, the product of a series of rifting events spread over 200 million years. The Tethys, which we do not think of at all because it exists now only in remnants and fossil records, was once the great seaway of the Mesozoic world, and it is mostly gone, consumed by the movements that opened the oceans we know. The world's oceans are not permanent. They are phases in a cycle that has been running since the Earth first had a solid surface, and they will continue to change long after the particulars of our moment have been folded into rock. But we are following life as well as rock. And it is now, in the long unzipping of these oceans and the drift of the fragments of Gondwana, that the story of life on Earth begins to take the shape we recognize. The particular, puzzling, beautiful distribution of animals across the modern world that requires an understanding of deep time and moving continents to make any sense of it all. Begin in the south. Begin with a lineage of animals that would come, in the fullness of time, to define an entire continent in the popular imagination. Marsupials carry their young in pouches. This much is known, this much is the thing that separates them most visibly from the placental mammals that dominate most of the rest of the world, the category of mammal that includes, among many others, the reader of this narration lying still in the dark. Placental mammals develop their young inside the body, connected by a placenta that transfers nutrients across a long gestation. Marsupials do something different. They give birth to young that are, by placental standards, astonishingly underdeveloped. Tiny, almost embryonic creatures that crawl, guided by instinct alone, from the birth canal to the pouch, where they attach to a nipple and continue their development outside the body in the protected environment of the pouch. A newborn kangaroo, a joey, is about the size of a jelly bean. It is blind, its hind legs are barely formed, and yet it makes this journey, this climb through its mother's fur to the pouch under its own power with a reliability that has been perfected over millions of years of evolution. This is one reproductive strategy among several that mammals have evolved. It is not inferior, it is simply different, and in the environment where it became dominant, it worked well enough to fill an entire continent with extraordinary variety. But where did marsupials come from? The answer is not Australia, despite everything the modern distribution of the animals might suggest. The oldest marsupial fossils known to science come not from Australia but from North America and China. The lineage is old enough that in the Cretaceous period, marsupials and their relatives were widespread across the northern parts of the world, living alongside the placental mammals that would eventually come to dominate those regions, and alongside the dinosaurs that still walked the Cretaceous Earth. How, then, did they come to be so overwhelmingly concentrated in Australia? The answer runs through Antarctica. Not the Antarctica of ice and blizzard and featureless white expanse that we know today, but an older Antarctica, an Antarctica that most people never encounter in their imaginations because it is so thoroughly unlike the continent that exists now. When marsupials were dispersing southward, Antarctica was temperate. This is not a small qualification. Antarctica, positioned at the bottom of the world, was nevertheless clothed in forest. Fossil evidence. And here, the distinction between rock and life dissolves completely because the rock is the life, is the preserved record of trees and ferns and the creatures that lived among them. Tells us that Antarctica, through much of the Cretaceous and into the early Paleogene, was covered by cool temperate to even warm temperate vegetation, by trees whose relatives still grow today in southern South America and in New Zealand and in Tasmania, southern beech, tree ferns, conifers, Dinosaurs walked those Antarctic forests, marsupials moved through them, and because Gondwana was still partly connected because the pieces had not yet fully separated, there was land to walk across. The route ran from South America, where marsupials, moving southward from North America through whatever land connections existed, into the forested landscapes of what is now the Antarctic Peninsula, and from there across a land connection that no longer exists in any form we would recognize into what would become Australia. This was a terrestrial route, not a crossing of open water. It was a corridor of forest and temperate land connecting three pieces of what had been Gondwana, maintained as long as those pieces remained close enough for land animals to move between them. The corridor did not last forever. Australia began separating from Antarctica approximately 45 to 35 million years ago. This was in the Eocene, in the epoch that followed the asteroid winter and the extinction at the end of the Cretaceous, in the warm, gradually cooling world of the early Cenozoic. The separation was not sudden. Rifting is never sudden. But over the millions of years of the Eocene, the gap between Australia and Antarctica widened from a narrow seaway into a genuine ocean barrier, and eventually into the body of water we now call the Southern Ocean. And when that gap became too wide to cross, the animals on either side of it were stranded. The marsupials in Australia were stranded on the right side of that gap, or rather, they were stranded on a continent of their own, a landmass that was drifting northward, away from the pole, into warmer latitudes, carrying its cargo of life away from the rest of the world. And the rest of the world, the placental mammals that were diversifying and spreading across Eurasia and Africa and North America in the Eocene and Oligocene, could not follow. The ocean was too wide. The crossing was impossible for land animals. Australia was sealed. What happened next over the tens of millions of years that followed is one of the most extraordinary episodes in the history of life on this planet. With almost no competition from placental mammals, because the only placentals that managed to reach Australia in significant numbers were bats, which could fly across the water, and rodents, which arrived much later by some combination of island hopping and rafting. The marsupials of Australia were free to do something that isolated lineages on isolated continents always do eventually, given enough time. They radiated. Radiation, in evolutionary biology, means the branching and diversification of a lineage into a wide range of ecological roles, each branch adapting to a different way of life. It is what happens when a group of animals finds itself in an environment full of unoccupied ecological space and relatively free of the competitors and predators that might otherwise constrain their evolution. The marsupials of Australia, cut off from the rest of the world's mammal fauna, found themselves in exactly this situation. And they responded over millions of years by producing an array of forms that, viewed from the outside, reads like a parallel evolution of the ecological roles that placental mammals were simultaneously filling on the other continents, but produced from a different starting point, through different pathways, ending in forms that are recognizably similar in function while being unmistakably different in biology. The grazers of Australia and the animals that fill the ecological role of cattle or horses or deer on other continents, the large herbivores that process grasses and tough vegetation in bulk, became kangaroos and wallabies. The macropods, named for their large feet, their distinctive bounding locomotion, the remarkable efficiency with which they move across open ground. A large red kangaroo can cover more than 8 meters in a single bound, can sustain speeds of around 50 kilometers per hour for short bursts, and moves more efficiently at higher speeds than at lower ones because the tendons in its hind legs store and return energy like springs. This is not what a horse does, not what a deer does, but it occupies something like the same ecological role in the landscape. The grasslands of Australia have a large, abundant grass-processing herbivore. On Australia, that herbivore has a pouch. The insectivorous niche, the role of small, underground, insect-eating mammal filled on other continents by moles, is filled in Australia by the marsupial mole Notoryctes, a creature so thoroughly adapted to life beneath sandy deserts that it has no functional eyes, has lost its external ears, and moves through loose sand as a swimmer moves through water. Compare it to the golden moles of Africa or the true moles of Eurasia. The adaptations are strikingly similar, with the reduced eyes, the powerful forelimbs or hind limbs modified for digging, the streamlined body, the absence of features that would catch on the soil. Same problem, different lineage, similar answer. The marsupial mole is not closely related to any true mole. It arrived at the same form because the same pressures, applied to a mammalian body over millions of years, tend to produce similar solutions. This is convergent evolution, the deep logic of natural selection expressing itself in parallel, on separate continents, in separate lineages, producing forms that are echoes of each other across the unbridgeable water. And then there was Thylacoleo. The name means in the Latin that scientists have used to classify living things since Linnaeus formalized the practice in the 18th century, marsupial lion, and the name is apt in a way that goes beyond mere convention. Thylacoleo carnifex, the meat-cutting marsupial lion, was a large predatory marsupial that lived in Australia from the Pliocene through to the Pleistocene, surviving until perhaps as recently as 30 to 40,000 years ago. It was powerfully built, with forelimbs suited to grappling and holding prey, with a bite force that, relative to its body size, has been estimated as one of the strongest of any mammal known from the fossil record, not excepting the largest bears, not excepting the great cats. It weighed perhaps 100 to 160 kilograms. It climbed trees. It was almost certainly an ambush predator, using cover to approach and overwhelm prey larger than itself. It was also a marsupial. It raised its young in a pouch. Its closest living relatives are not lions, not leopards, not any of the great cats of Africa or Asia or the Americas, but wombats and koalas, the roly-poly, eucalyptus-scented vegetarians of the Australian bush. Evolution, given an isolated continent and enough time, built a lion out of the lineage that also built a koala. The distance between those two outcomes, measured not in time but in the strangeness of what natural selection can accomplish when a continent becomes a closed experiment, is difficult to fully absorb. And then there was the thylacine. The thylacine, Thylacinus cynocephalus, the dog-headed pouched one, is the animal that of all the creatures produced by Australia's marsupial radiation most powerfully illustrates the principle of convergence. It looked like a dog, not superficially, not in some vague sense that requires squinting and imagination, but genuinely, compellingly, startlingly like a dog with a long, low body, a stiff tail held straight behind it, a distinctive long jaw, and an overall silhouette that, in a black and white photograph or a grainy film strip, reads immediately as canine. The striped markings across its lower back and hindquarters were distinctive, giving rise to its popular name, the Tasmanian tiger, though it was not a tiger either, in any biological sense. It was neither dog nor tiger. It was a marsupial, carrying its young in a pouch like the kangaroo and the koala, related to them rather than to any of the animals it resembled. It had evolved the dog-like form independently on a continent where no true dogs existed, because the ecological role of a medium-large cursorial predator, an animal that pursues prey over ground, using endurance and intelligence and a long-jawed grip, is a role that tends to be filled, given mammalian raw material, and enough time by something that ends up looking rather like a dog. This is not a coincidence. It is the logic of selection made visible in two lineages that reached the same destination from entirely different origins: the placental wolf and the marsupial thylacine. Two answers to the same question written in different biological languages, arriving at a form so similar that the untrained eye cannot immediately distinguish them. The thylacine was once widespread across Australia and New Guinea. Fossil evidence and Aboriginal rock art suggest it ranged across the continent for tens of thousands of years before its decline, which accelerated sharply after the arrival of human beings, and later of dingoes. Placental dogs introduced to mainland Australia by humans roughly 3,000 to 4,000 years ago. The combination of hunting and competition drove the thylacine to extinction on the mainland, leaving it confined to the island of Tasmania off Australia's southeastern coast, where it survived into the 20th century. This is not ancient history, not a loss absorbed so long ago that it exists only in the fossil record and the geological imagination. The thylacine was still alive in living memory. It was photographed. It was filmed. A handful of short, grainy, heartbreaking film clips exist, showing the animal pacing in its enclosure, its jaws opening to a remarkable gape, its striped hindquarters and stiff tail, the particular quality of its movement that was neither quite dog nor quite anything else but itself. It was held in zoos. The last known wild individual was reportedly shot in 1930 in a world where the automobile was common and the radio was a household fixture. And the last captive individual, a male, held at the Hobart Zoo in Tasmania, died on the night of the 7th of September 1936. His name, or the name that has been given to him retrospectively in the decades since his death, was Benjamin. Benjamin died in his enclosure on a cold September night, reportedly because he had been accidentally locked out of his sheltered sleeping quarters and exposed to the cold. He was not the subject of particular attention or mourning at the time of his death. The zoo noted his passing. The species was declared protected, but only weeks after he died, in a piece of timing that might be read as a parable about human attention and the moment of loss. And then the thylacine was gone. The marsupial wolf, the dog-headed pouched one, the animal that two separate continents on opposite sides of the world had independently decided to build when they needed something to fill the role of a running predator. Extinct, the last individual of its kind, dying alone on a September night in a zoo in the capital of Tasmania. The extinction of the thylacine is not the end of the story that Gondwana was telling. It is a chapter within it, a chapter about what happens when the isolation that produced something extraordinary is punctured, when the closed experiment of a continent is opened, and the carefully evolved, locally adapted fauna encounters something it did not evolve to face. But we will come to that in other places and in other contexts. For now, the thylacine stands as the clearest single image of what continental drift accomplished in Australia. It produced a wolf that was not a wolf, a predator that reached the same form as the dogs and the wolves of the northern world, through a completely independent evolutionary journey, beginning from a completely different starting point, in a place that had been sealed from the rest of mammalian diversity for tens of millions of years. Australia is, in this sense, not merely a continent with unusual animals. It is the proof, living, breathing, in some cases, sadly, no longer breathing proof, that the same evolutionary outcomes can be reached from different starting points when the same pressures apply, and that continental drift in separating land masses and their passengers from each other set in motion experiments in evolution that no single, connected world could ever have run. The pouch inherited the continent, and on that continent, the pouch built wolves and lions and moles, and the great bounding grazers of the open plain, all from a starting point that its counterparts on other continents had taken in entirely different directions. The Southern Ocean now fills the gap where the land connection between Australia and Antarctica once ran. It is cold and deep, and the winds that move across it are the strongest on Earth. The roaring 40s and the furious 50s, the great westerlies that circle the pole unimpeded by any landmass, generating swells that travel all the way around the world before they meet themselves again. Nothing crosses it. No land animal has walked across the seafloor that once connected the temperate forests of the Cretaceous South. The corridor is closed and has been closed for tens of millions of years, and the animals on either side of it, the marsupials of Australia and the placentals of the remaining world, have been becoming progressively less recognizable to each other ever since. The world that Gondwana scattered is not done scattering. There are more pieces drifting to their own particular destinies, carrying their own particular cargo of life, becoming their own particular experiments in what evolution can do when it is given an isolated stage and an unhurried span of time. Madagascar is waiting. India is in motion, building speed toward a collision that will raise the roof of the world. South America is becoming its own island of monsters deep in the southern hemisphere, cut off by ocean on all sides. And Antarctica, the bridge that closed behind the marsupials as they crossed into Australia, is drifting toward the pole, toward the cold and the ice and the long burial of everything that once lived there. Each of these fragments has a story. Each of them is, in itself, a demonstration of what the slow tearing apart of a supercontinent accomplishes in the biological world, not merely a rearrangement of geography, but a multiplication of possibilities, a branching of the tree of life along lines drawn not by competition or predation or climate alone, but by the movement of rock, by the engine of the mantle, by the patient, indifferent mechanism of convection carrying plates at the speed of a growing fingernail toward destinies that no living thing aboard them could have anticipated or even perceived. Australia drifts north through the Eocene and Oligocene and Miocene into warmer and drier latitudes, the marsupials upon it diversifying and filling the land, the continent becoming more arid in its center as the forests give way to scrubland, and then to desert, and then to the vast, red interior that we know today. It drifts north still. It is still moving, still approaching Asia, its northern edge beginning to crumple where it meets the islands of the Indonesian archipelago. An encounter, still early in geological terms, that is the beginning of something whose full consequences lie far in the future, beyond the span of any human reckoning. But the marsupials do not know this. They live their lives in the present, as all living things do in the particular climate and vegetation and ecological context of their particular moment. The kangaroo bounding across the red plain in the afternoon light, the wombat turning in its burrow in the cool of the evening, the possum moving through the canopy of a eucalyptus forest in the dark. None of them carry the weight of 200 million years of history in any conscious sense. They are simply themselves, the products of what the Earth has done, living in a world shaped by forces whose magnitude is entirely incommensurate with the scale of a single life. But we can carry it. Lying still in the dark, in the quiet hours before sleep, we can hold the whole long arc of it, the supercontinent assembling, the rift beginning, the Atlantic opening in 3 slow stages across 140 million years, the Tethys closing in exchange, the fragments of Gondwana pulling apart, the marsupials crossing the forested Antarctic corridor before it sank beneath the Southern Ocean, the Australian continent sealing itself away and becoming, in its isolation, the most extraordinary living experiment in parallel evolution that the Earth has ever run. The night is deep. The drift continues, and there is still so much more of the story left to follow. Madagascar was an island long before it thought of itself as anything at all. It sits in the Mozambique Channel today like a comma in the sea, separated from the eastern coast of Africa by roughly 400 kilometers of deep, warm water, and it wears its isolation the way an old country wears its history, not as something imposed from outside, but as the very substance of what it is. The animals that live there, the plants that carpet its different zones from the dry, spiny thickets of the south to the rainforests of the east, the lemurs watching from the branches with their wide, deliberate eyes, all of it has the quality of a world that developed its own logic, in its own time, without reference to anything happening on the larger continents nearby. That isolation began approximately 160 million years ago when Madagascar tore away from the eastern flank of Africa and began moving slowly south and east through the warming waters of what would become the Indian Ocean. The rift that separated it was not sudden. Nothing in this long story is sudden. It was a slow parting, a widening of the crust, magma rising to fill the gap, new ocean floor cooling, and recording the direction of Earth's magnetic field as it hardened, the same process, the same patient mechanism that was at that very time opening the South Atlantic to the west, and would, in the fullness of geological time, sever nearly every great southern landmass from every other. Madagascar was simply one of the earliest pieces to come loose from the dissolving body of Gondwana, and when it moved, it carried with it whatever life happened to be living there at the moment of the parting. But here is the detail that makes Madagascar's story stranger and more wonderful than a simple account of separation would suggest. The animals most associated with the island today, the lemurs, those ancient relatives of the primates, the ones with the ringed tails and the golden eyes and the social complexity that can fill hours of careful watching, did not ride the island away from Africa. They were not already there when Madagascar broke free. The island separated from Africa 160 million years ago, and the ancestors of the lemurs did not reach Madagascar until somewhere between 50 and 60 million years ago, which means that for roughly 100 million years, Madagascar sat in the sea, an island, and the creatures that would eventually define it in the popular imagination had not yet arrived. And yet they arrived, somehow across 400 kilometers of open ocean, in an era long before anything resembling a boat existed. The small primate ancestors of what would become every lemur species on Earth made the crossing. The current understanding, pieced together from molecular clocks, from the reconstructed positions of the ocean currents at the relevant time, from what we know about the biology of small mammals under stress, is that they rafted. A mat of vegetation, uprooted perhaps by a river in flood or torn loose by a storm from the African coast, carried a small group of animals, perhaps a pregnant female, perhaps a handful of individuals, out across the Mozambique Channel. The currents at that time, 50 to 60 million years ago, may have run in a direction more favorable to the crossing than they do today, shortening the effective distance, or at least making the drift survivable. And so, against all ordinary probability, the crossing happened. What greeted them when they arrived was an island with no monkeys, no apes, no large carnivores of the kind that shaped primate behavior elsewhere in the world, no elephants, no antelopes. An island, in effect, cleared of all the pressures that had defined primate life in Africa and would define it in Asia. What they found was open space, ecological space, the emptiness of a world waiting to be filled, and they filled it. Over the 50 to 60 million years since that unlikely crossing, the descendants of that small founding population radiated into something extraordinary. Today, Madagascar is home to roughly 100 living species of lemur, ranging from the tiny mouse lemur, small enough to fit in the palm of a hand, the smallest primate on Earth, up through the larger, more socially complex species like the ring-tailed lemur and the indri, whose call carries through the forest in the early morning like something between a song and a warning. They occupy different ecological roles, different layers of the forest, different times of day and night. Some eat fruit, some eat leaves, some eat insects and small vertebrates. Some sleep in groups for warmth, some are largely solitary. The diversity is a direct measure of the time they have had and the freedom they have had to diverge. But the living species are only part of the story, because alongside the lemurs that still exist, there were, until very recently in geological terms, species that carried the principle of lemur radiation to even more extraordinary extremes. The gorilla-sized Archaeoindris, the largest primate ever to have lived on a small island, moved through Madagascar's forests. An animal the size of a male gorilla, presumably slow-moving and peaceful, browsing on vegetation in the way that giant mammals do when no predator has shaped them into speed or wariness. There were the koala lemurs, Megalodopes, with their gripping feet and their slow arboreal life. There were the sloth-like lemurs that hung from branches and moved with an unhurried deliberateness that the forest rewarded because nothing was hunting them. And there was the elephant bird, Epionis, not a lemur, but a product of the same isolation, a flightless bird that stood 3 meters tall and laid eggs larger than those of any other known bird, holding more liquid than 160 chicken eggs combined. It was the heaviest bird ever to have existed. It walked the coastal forests and the open grasslands of Madagascar until humans arrived. The humans arrived approximately 2,000 years ago. In geological time, that is less than a breath ago, the thinnest shaving from the end of the record. And in the 2,000 years since that arrival, the great majority of Madagascar's largest animals have vanished. The giant lemurs are gone, Archaeoindris is gone, the elephant bird is gone. The subfossil bones remain, preserved in caves and lake beds and dry riverbeds, a catalogue of what was lost and how quickly. Over 90% of Madagascar's species still live nowhere else on Earth. The island's endemic rate remains astonishing. But the largest, the most visible, the most magnificent expressions of what island isolation could produce have been removed, mostly within the last 1,000 years. It is worth resting with that for a moment. 50 to 60 million years of evolution, 50 to 60 million years of the lemurs quietly becoming everything they became in the absence of competition and predation, and then 2,000 years. The arithmetic is not kind, but it does not erase what was accomplished in the longer time. The island itself remains, and the smaller lemurs in their hundreds of species remain, and the record of the larger ones persists in the bones and in the molecular signatures that can now be read from ancient DNA and in the shape of the ecosystem that was built around them. Madagascar is still one of the most ecologically distinctive places on Earth. The drift that made it possible is still one of the most consequential events in the history of life. While Madagascar was becoming the world's lemur ark, somewhere to its northeast, another fragment of Gondwana was undertaking a journey of an entirely different character. India, after separating from Madagascar approximately 88 million years ago, began moving north. And it did not move north slowly, not by the standards of plate tectonics. The Indian plate accelerated across the widening Indian Ocean at somewhere between 15 and 20 centimeters per year, which may sound like nothing, and which in the terms of ordinary human experience is nothing less than the rate at which hair grows. But in the context of plate motion, where the typical rate is perhaps 2 to 10 centimeters per year, it was extraordinary. Some estimates suggest it may have moved at something close to twice the speed of other major plates during its most rapid phase. Geologists have debated the reasons for this: the thinning of the plate itself, the pull exerted by the subducting oceanic crust ahead of it, and the influence of the Réunion hotspot, a fixed plume of heat rising from deep in the mantle, which is thought to have buoyed and perhaps lightened the plate during its northward run. The Réunion hotspot is still there. Today it sits beneath the island of Réunion in the Indian Ocean, producing the volcanic activity that makes the island geologically alive. But 66 million years ago, the Indian plate was passing directly over it, and the consequences were anything but tranquil. As the plate moved north over the stationary plume, magma punched upward through the crust and poured out across what is now the western and central part of the Indian subcontinent in volumes almost incomprehensible by the standards of historical volcanic events. These were the Deccan Traps, a series of flood basalts that at their greatest extent may have covered an area approaching 500,000 square kilometers to a depth of more than 2 kilometers, built up layer by layer over hundreds of thousands of years as eruption followed eruption followed eruption. The timing of the Deccan Traps matters enormously because the Deccan eruptions were at or near their peak at roughly the same moment that another catastrophe was unfolding on the other side of the world. The Chicxulub asteroid, an impactor perhaps 10 to 15 kilometers across, struck the shallow sea of what is now the Yucatan Peninsula of Mexico approximately 66 million years ago, releasing energy equivalent to billions of nuclear weapons in a single geological instant, sending a pulse of superheated rock and vapor into the atmosphere, initiating wildfires across entire regions and ultimately blanketing the planet in dust and debris that blocked sunlight for months to years. The non-avian dinosaurs, which had dominated terrestrial ecosystems for more than 150 million years, did not survive the combination. The end Cretaceous extinction, to the most famous mass extinction in popular consciousness, unfolded at the intersection of these two catastrophes, the Deccan eruptions and the Chicxulub impact. And the precise contribution of each to the extinction is still debated by paleontologists and geophysicists working with the accumulated data of decades of fieldwork. But the Indian plate did not stop at the Deccan Traps. It continued north, the ocean floor ahead of it subducting beneath Asia, the gap between India and the Asian continent narrowing over millions of years at its relentless pace. And somewhere between 50 and 40 million years ago, the leading edge of India, the old continental crust that had been part of Gondwana, carrying the sediments and the fossils of everything that had once lived on it, met the southern margin of Asia. What happened at that meeting is still happening. When two pieces of continental crust collide, not an oceanic plate sinking beneath a continental one, but two continents both buoyant, neither willing to subduct. The result is compression. The crust crumples, it thickens, it buckles upward in folds and thrust faults, rock that was once horizontal becoming vertical, sediment that was once ocean floor rising toward the sky. This is what the Himalayan collision was and is, the ongoing collision between two great masses of continental crust, neither of which can sink, and both of which have been pushing against each other for tens of millions of years. The Himalayas are still rising today at roughly 5 to 10 millimeters per year. Erosion keeps pace with uplift to some degree, which is why they are not taller, and the collision that produces them is no closer to resolution than it was when it began. And somewhere in the Himalayas near the summit of Mount Everest, there is a layer of rock that carries within it one of the most quietly remarkable facts in the whole long story of the moving Earth. The limestone near the peak, the Komalangma Formation, the Tethyan sedimentary sequence, was deposited at the bottom of the Tethys Ocean, the warm, shallow sea that once lay between the northern half of the old supercontinent and the southern. It was laid down in the light-filled shallows of a tropical sea, built up grain by grain from the shells and skeletons of marine organisms, crinoids, brachiopods, trilobites, and their relatives, that lived and died in that warm water tens of millions of years before the Indian plate began its northward journey. It was ocean floor, and now it is the highest point on Earth. The summit of Everest, at more than 8,800 meters above sea level, is made of rock that formed at the bottom of an ocean that no longer exists. The sea creatures whose remains are locked in that limestone never imagined, in whatever way that phrase can apply to creatures without imagination, that their shells would one day form the roof of the world. They simply lived and died in their warm, shallow sea, sank to the bottom, and were slowly compressed and lithified into stone. And then the Indian plate moved, and the Tethys closed, and the ocean floor was lifted, and over tens of millions of years the limestone rose until it stood higher than any other rock on the planet. The climbers who have reached that summit, the ones who have stood in the brutal cold and thin air at the top of the world and looked out across the mountains spreading in every direction, have stood on an ancient seabed, on the bones of sea creatures, on the evidence of the Tethys Ocean, which was already closing while the dinosaurs still walked, which finished closing as the Himalayas built, and which exists now only in fossils and in the record of marine sediments heaved improbably into the sky. To the west, to the south, to the entire far hemisphere, another fragment of Gondwana was living out its own isolation in a very different register. South America, after its separation from Africa, had become what paleontologists sometimes call the island continent, a landmass completely surrounded by ocean, cut off from North America by the seaway that separated the two, cut off from Antarctica as that continent drifted toward the pole, and cut off from any regular exchange with the larger world. It was not Antarctica's isolation, which would become profound and frozen. It was a milder, warmer isolation, a continent in the tropics and subtropics with a vast range of climates and habitats, and it was during this isolation, which lasted for tens of millions of years, that South America did something extraordinary with the life it contained. In the absence of the placental carnivores that were filling those roles in the northern continents, no lions, no wolves, no saber-toothed cats, South America evolved its own answers. The terror birds, the Phorusrhacidae, were perhaps the most spectacular. They were flightless birds, the descendants of flying ancestors, which over millions of years had lost the wings that flight requires and redirected that evolutionary investment into size and strength and speed. The largest of them stood approximately 3 meters tall. They ran on powerful legs and struck with hooked beaks, capable of delivering blows that could kill or stun large prey. They were the apex predators of South American grasslands for tens of millions of years. Not a wolf, not a big cat, but a bird, a descendant of the same great lineage that had survived the end Cretaceous extinction precisely because the smaller, flying members of the avian line had been nimble enough to survive what the large ground-dwellers could not. Alongside the terror birds were the glyptodonts, relatives of the armadillos still alive today, but built to an entirely different specification. Car-sized animals, some of them, covered in a domed armor of fused bony plates, their tails encased in a club or a ring of bone that could be swung in defense or conflict. They were among the most heavily armored mammals that have ever existed, lumbering tanks of the pampas, grazing on tough vegetation with a stolid deliberateness that the absence of effective predators permitted. And there were the giant ground sloths, not the small, slow, arboreal sloths of the modern rainforest canopy, but their immense relatives, some of which stood on their hind legs to a height of 6 meters to strip the high branches of trees. They left their claw marks on cave walls in South America, preserved in the paleontological record, evidence of animals so large that almost nothing could threaten them. These creatures, and the many others that accompanied them in South America's isolated menagerie, had no equivalent anywhere else in the world. They were South America's answers to questions that evolution poses on every continent. Who will eat the plants? Who will hunt the plant eaters? Who will fill the niche of the large-bodied grazer? Who will occupy the role of the top predator? And South America answered them in ways that were different from anywhere else, because the animals available to give those answers were different, shaped by a different evolutionary history going back through the long isolation of the island continent. And then approximately 3 million years ago, the isolation ended. The Isthmus of Panama, the narrow neck of land connecting Central America to South America, rose slowly from the sea as the Caribbean and Pacific tectonic plates shifted and the ocean floor between them was pushed upward until it broke the surface. This was not a single dramatic event. It was a gradual shoaling of the seaway, a shallow marine connection narrowing over millions of years until it finally closed completely, and the two American continents, North and South, were joined by land for the first time in tens of millions of years. The moment had enormous consequences, not just for the animals on either side of it, but for the oceans too. The closure of the seaway between the Atlantic and the Pacific altered ocean circulation in ways that contributed to the onset of the Pleistocene Ice Age. But for the purposes of this story, it is the biological consequence that matters. What followed is called the Great American Biotic Interchange. Animals from the north moved south and animals from the south moved north across the new land bridge in what was probably not a sudden flood, but a sustained exchange over hundreds of thousands and millions of years. From the north came the placental carnivores that South America had never encountered, ancestors of today's jaguars and pumas and mountain lions, ancestors of foxes and wolves, mastodons and horses. These animals moved into a continent whose fauna had been shaped entirely without them, and the encounter was not easy for South America's endemic lineages. The terror birds disappeared, the glyptodonts disappeared, the giant ground sloths declined and eventually vanished, though some survived long enough to encounter humans arriving from Asia via the Bering Land Bridge. Many of the native South American hoofed mammals, the unique lineages that had evolved without reference to anything in the northern world, were replaced. A few South American lineages moved the other way and succeeded in the north. The ancestors of the opossums, the only marsupials native to North America, came from the south. The armadillos that have spread into the southern United States came from the south. The porcupines that inhabit North American forests are South American in origin. The exchange ran in both directions, but it ran harder in one than the other, and South America's long experiment in isolated evolution was, for its most distinctive participants, largely ended by the connection that 3 million years of geological process had eventually created. There is a quality to this story that recurs across all the isolated land masses. The isolation is productive, extraordinarily, wildly productive, generating life forms of a kind that could not have appeared in a connected world, because connectivity brings competition, and competition prunes the most experimental solutions. But the isolation also creates fragility. The unique fauna of an isolated continent or island is unique precisely because it evolved in the absence of the forces that shaped life elsewhere. And when those forces finally arrive, whether in the form of a land bridge closing or a human population setting foot on an island for the first time, the encounter is often devastating and almost always irreversible. The elephant bird on Madagascar, the terror birds in South America, the giant lemurs. The remarkable menagerie of isolated worlds is also, wherever the record is complete enough to follow, a chronicle of loss. Antarctica's story is the most complete and the most final of all these isolations. We have already followed the marsupials through the Antarctic corridor before the continent's temperature began to fall, before the ice began to build, before the forest that once grew there gave way to the open tundra and then to the glacier. But the mechanism of Antarctica's freezing is worth dwelling on, because it is as elegant and as consequential as anything else in this long account. When Antarctica was still connected to South America, there was no gap between them at the southern end of the world. The circulation of the Southern Ocean was interrupted by that connection. The water could not complete a circuit around the pole without encountering the land, and so it did not. And the water that could not circulate freely could exchange heat with the lower latitudes, and Antarctica, though cooling as it drifted south, was still warmed to some degree by that exchange. Then approximately 34 to 30 million years ago, the Drake Passage opened. The separation of Antarctica from South America, the final severance of that connection, the widening of the gap between the tip of South America and the Antarctic Peninsula to the south, allowed the ocean to flow unimpeded around the entire continent. And when it did, the Antarctic Circumpolar Current was born. This current, the largest ocean current on Earth, runs continuously around Antarctica, moving volumes of water that dwarf any other current, and it acts as a thermal barrier, an encircling moat of cold-moving water that effectively cuts Antarctica off from the warmer waters to the north. The heat exchange that had been warming the continent was interrupted. The temperature fell, the ice began to accumulate, and Antarctica, which had been forested and alive, which had nurtured marsupials and dinosaurs and temperate plants, sealed itself beneath a growing ice sheet that today holds approximately 60% of the world's fresh water. The forests are still there in a sense. The coal seams that geologists have found in Antarctica are the compressed remnants of those ancient forests, the vegetation of a warmer world transformed over millions of years by heat and pressure into the black rock that carries their carbon. The dinosaur bones are still there, in the rock exposed along the mountain ranges that push through the ice. The whole forested living world that Antarctica once was is preserved in the layers beneath the ice, a record of everything the continent was before the Drake Passage opened and the circumpolar current sealed it away. New Zealand had taken a different path to isolation and arrived at a different kind of world. It had separated from the Australian and Antarctic plate somewhere between 85 and 80 million years ago. Before Australia completed its own separation, before many of the events this story has followed had even begun. And in its long isolation, it had developed something that could only have arisen in the absence of land mammals. It became a world of birds. On most continents, birds share their ecological space with mammals. Mammals run the ground, occupy the burrows, perform the roles of grazers and browsers and hunters and scavengers. Birds, for the most part, are the masters of the air. But in New Zealand, where almost no native land mammals existed, the only native ones were bats, which had flown there. The birds had the ground. They had the burrows. They had the roles of grazers and browsers and, in at least one case, the role of apex predator. The moa were the grazers and browsers, a group of flightless birds ranging from the size of a turkey up to species that stood 3 meters tall and weighed 250 kilograms. They were the largest birds in New Zealand's ecosystem, the equivalent of the deer and the cattle of other continents, moving through the forests and grasslands and cropping the vegetation at heights ranging from ground level to the upper branches of shrubs and small trees. The kiwi, small and nocturnal and probing the soil with a bill fitted with sensitive nostrils at its tip, an adaptation for finding earthworms and invertebrates in the leaf litter, was at the other end of the size spectrum, doing underground what a hedgehog or a small mammal would do elsewhere. And above them, hunting the moa, was the Haast's eagle, the largest eagle known to have existed, with talons the size of a modern tiger's claws and the power to strike and kill animals many times its own weight. This was a world that had arrived at its own answers to ecology's standing questions, using only the lineages that had been present when New Zealand separated, plus the occasional wind-blown or ocean-crossing arrival over the subsequent 80 million years. It was, like Australia and Madagascar and the isolated South America, an experiment running in parallel with the rest of the world, producing, by the same evolutionary logic applied to different materials, a set of solutions that were recognizably functional and yet entirely unlike anything the connected continents had produced. And then, like South America, like Madagascar, like so many of the isolated worlds, it met the human world. In this case, Polynesian navigators arrived in approximately the 13th century, and in the centuries following their arrival, all of the moa species went extinct. The Haast's eagle, dependent on the moa as its prey, followed them. The pattern holds. The isolation that made these worlds extraordinary also made them vulnerable in ways that the connected continents, which had been shaped by the continuous pressure of competition and predation, were not. The unique is also the fragile. The scattered ratite birds tell this whole story in miniature, distributed across what was once a single landmass. The ostrich in Africa, the rhea in South America, the emu and cassowary in Australia, the kiwi and the now-extinct moa in New Zealand, the now-extinct elephant bird in Madagascar. All of them are related, all of them are flightless, and all of them arrived in their current positions not by flying there, but by being carried slowly over millions of years on the drifting fragments of Gondwana. Their distribution is a map of the breakup, written in living and recently living animals, legible to anyone who knows how to read it. Wallace's line runs through the sea between Bali and Lombok, between Borneo and Sulawesi, a line so sharp that it separates two entirely different faunal worlds within a few dozen kilometers. To the west of the line, Asian animals, placental mammals, the world of the connected Eurasian landmass. To the east, the animals of Australasia, marsupial-influenced, shaped by the long isolation of the Australian plate. The line was identified by Alfred Russel Wallace, who noticed, traveling through the Indonesian archipelago in the 19th century, that the animals on one side of a particular stretch of water were completely unlike the animals on the other side, despite the narrow gap between them. He did not yet have the theory of plate tectonics to explain it, but he saw the boundary clearly, and what he was seeing was the boundary between two worlds that drifting had separated by a deep ocean trench that no land bridge had ever bridged. Wallace's line is drift made visible in the present. It is the seam between two great chapters of Gondwana's dissolution, preserved in the distribution of living animals, observable to anyone with a field notebook and the patience to look. And the Earth is not finished. The process that assembled Pangaea and tore it apart has not ended, and the current arrangement of the continents is no more permanent than any of the arrangements that preceded it. The East African rift is the Atlantic of the future, a long fracture running south from the Afar Triangle in Ethiopia, through Kenya and Tanzania, and toward the south of the continent, slowly pulling East Africa away from the rest of the continent, slowly widening as magma rises and the crust thins and the rift valley deepens. It will take tens of millions of years, but the process is underway, and the long-term consequence of that process, assuming it continues, is a new ocean, a new narrow sea widening into something larger, East Africa becoming its own island continent, beginning its own experiment in isolation. The Atlantic is still widening at roughly 2.5 centimeters per year. The Pacific is shrinking as the plates that compose its floor subduct beneath the continents on its margins, the great subduction zones of the Western Americas and the island chains of the Pacific. In 200 to 250 million years, a span of time as great as the entire history of the dinosaurs, the next supercontinent is expected to form. Whether it will be what geologists call Pangaea Ultima, forming as the closing Atlantic brings the Americas back into contact with Europe and Africa, or Amasia, forming as North America and Asia close the Arctic Ocean between them, or some other configuration given other names, Orica, Novo Pangaea, is a matter of ongoing modeling and debate. What is not in doubt is that the cycle continues. The supercontinent that will form in the deep future will not be Pangaea. It will be something new, assembled from pieces that are themselves the products of 200 million years of drift and collision and separation, carrying on their surfaces the descendants of animals that are today still separated by the oceans that Pangaea's breakup created. The lemurs of Madagascar, whatever their descendants will be in 50 million years. The marsupials of Australia, whatever forms they will have taken in the millions of years between now and the next assembly. The ratites, the birds that carried the southern continent story in their flightless bodies across the long geography of Gondwana's dissolution. All of it moving forward, changing, speciation continuing at its quiet pace, the engine of drift still running beneath everything, the mantles still convecting, the slabs still pulling, the ridges still spreading, the slow churning of the deep earth still doing what it has been doing for billions of years. And this, all of this, was the story being told beneath you all along. Beneath the ground you walked on today, beneath the city, or the countryside, or the ocean floor, if you are a creature of the sea, the plates are moving. Not at a pace you can feel in the span of a single life, not at a pace that announces itself in any ordinary hour, but moving. The same movement that carried Glossopteris across 5 continents in the leaves of a fern. The same movement that stranded the marsupials on their southern arc and set the lemurs rafting across the Mozambique Channel. The same movement that drove India north across an entire ocean and crumpled the Tethys seabed up into the sky so that the shells of ancient sea creatures now rest at the highest point on Earth, above the clouds, in the thin cold air where almost nothing lives. The continents drifted, and the life on them drifted with them. And in that drifting, in the slow, patient, implacable separation of one piece of land from another, in the widening of the water between them, in the millions of years of evolving in isolation that followed, the living world became what it is. The kangaroo and the wolf are not accidents of separate inspiration. They are both answers to the same question, given by evolution working on different materials in different places, separated by a movement of rock so slow that it took 2 centuries of scientific work to prove it had happened at all. The lemur and the monkey are both answers to the same question. The terror bird and the lion are both answers to the same question. Drift is not the backdrop to the story of life. Drift is one of the great authors of it. You have followed this story through the long dark, from the assembled supercontinent to its fracture, from the first cracks in the crust to the opening of 3 oceans in sequence, from the stranded marsupials to the racing Indian plate, from the Mozambique Channel crossing to the summit of the world. You have held in your mind, in the quiet hours before sleep, a span of time and transformation that no single human life can fully comprehend, and you have done so with patience and with stillness. If you feel moved to share where in the world you are listening from tonight, I would genuinely like to know. Whether you are in the southern hemisphere where the fragments of Gondwana still sit, or in the north where Laurasia left its pieces, or somewhere in between on crust that carries its own long history. Wherever you are, the ground beneath you has a story as old as this one, and older. Leave it in the comments. I read them. There are more slow journeys here, of this same unhurried kind, waiting for whenever you want them. The earth is still turning tonight, very gently. The plates are still moving, too slowly to feel. The Himalayas are still rising, 1 millimeter at a time. The East African rift is still widening, patient and inevitable. And somewhere, in the forests of Madagascar, a lemur sits in the dark in a tree that has never known anything but an island looking out at a world that has been shaped by forces it will never be asked to understand. You have done enough for one night. You have carried the whole long arc of it. 200 million years of drift and separation, of life becoming unrecognizable to itself across widening water. And now you can let it settle and be still. Let the wisdom settle soft, the rest will come on its own.